Welcome back to MEV Explained. Today, Generalized Frontrunners and the honeypot that turns them into prey in 3 acts. First, the bait, a transaction that looks like free money, then the trap, where a bot copies it and gets wrecked, and then the defense. And every act, we prove it 3 ways, on a diagram, in a test, and live on a public blockchain, following the tokens on Etherscan. Let's go. First, the idea. A generalized frontrunner is a bot that watches the mempool for any transaction that looks profitable, copies its call data, and runs that copy first with higher gas, stealing the profit without understanding it. It's pure copy-paste greed. Now a honeypot is bait built for exactly that bot. The Salmonella token we'll build looks like a normal valuable token, but it has a trick. When the honeypot's owner moves it, the full amount moves. When anyone else moves it, only 1% actually moves, yet the token still emits a transfer event for the full amount. So a bot that trusts the event or naive simulation sees a profitable move and pounces, and only afterward discovers the tokens were never really there. Let's build it. Okay, we build it in Foundry. Here is the skeleton of the Salmonella token, a normal looking ERC20 with balances, transfers, and the standard transfer event. The one function that hides the trap is the internal move, so let's fill it in. Here's the move function, and here's the whole trick. It figures out how much really moves. If the sender is the owner, the full amount, but if it's anyone else, only 1%. It updates the balances by that real amount. And then, on the last line, it emits a transfer event for the full amount, not the real one. That event is the lie. Any bot or explorer that trusts it believes the full amount moved. Let's watch it play out honestly first. Act 1, the honest move on the diagram. The honeypot's owner sends 1,000 Salmonella tokens to Bob because the sender is the owner, the full 1,000 really moves, and Bob really receives 1,000. The transfer event says 1,000, and this time the event is telling the truth. Everything looks completely normal. And that's the point. This is the bait that makes the token look legitimate and valuable. Now let's prove it. Here's the honest test. The owner mints 1,000 tokens and sends them to Bob. We print what the event claims moved and what Bob actually received. Watch them match. Run it. The owner moves 1,000. The event says 1,000 moved and Bob actually received 1,000. They match because the owner is the one moving. Honest and boring, exactly as bait should look. Now let's watch it on a real blockchain. We deployed this token to Sepolia, a public testnet, through my Chainstack node. Here's the owner's transfer, live and follow the token. Etherscan lists 1 transfer, 1,000 Salmonella from the owner to Bob. And because the owner moved it, 1,000 really did arrive, truthful, normal, tempting. Now watch a bot take the bait. Act 2, the trap on the diagram. A generalized frontrunner sees a profitable looking Salmonella move in the mempool and blindly copies it, moving 1,000 tokens, expecting to profit. But the frontrunner is not the owner, so under the hood, only 1%, 10 tokens actually moves, while the token still emits a transfer event for the full 1,000. The bot's own profit check reads that event, sees 1,000 and thinks it won. In reality, it committed guess and capital and got 10 tokens. The hunter just became the prey. Let's prove it. Here's this as the trap test. A front runner any address that isn't the owner moves 1,000 tokens to a sink. We print what the event claims and what actually arrived. Watch them split apart. Run it. The front runner moves 1,000. The transfer event value is 1,000. That's what Etherscan and a naive bot see. But the sink's real balance is 10. Only 1% actually moved. Same call, and the event and reality now disagree by 100 to 1. Now on chain, where it's even more convincing. Here's the front runners copied the transaction, live on Etherscan, and this is the whole episode in one picture. Etherscan's token flow says it plainly. 1,000 Salmonella transferred from the front runner to the sink. A copybot reading this sees 1,000 and celebrates. But that number comes from the emitted event, and the event is a lie. Because the front runner isn't the owner, only 10 actually moved. Don't take my word for it. Let's read the real balance. in the terminal, I ask the token for the sync's real balance, not the event, the actual stored balance, and it's 10. Etherscan showed 1,000, the chain state says 10, only 1% ever moved. The generalized frontrunner trusted the event, spent real gas and real capital to copy a profit that never existed, and walked away with almost nothing. That's the honeypot. Now let's defend against it. Act 3, the defense. The honeypot works because the bot trusted the transfer event or a naive simulation instead of checking reality. So the fix is simple. Never trust the event, verify the real balance. On the diagram, a careful integrator pulls the tokens, then reads its own balance before and after, and requires that it actually rose by the amount expected. Against the honeypot, only 10 arrive, so the check fails and the whole transaction reverts, no loss. And the deeper, real-world defense is private order flow. Send your profitable transactions through a private channel so a copy bot never sees them in the mempool in the first place. Let's build the balance check and prove it. Here's the fixing code. A SafeReceiver. Before pulling, it records its own balance, it pulls the tokens, then it reads its balance again and requires that the difference equals exactly the amount it expected. Against a normal token, that's always true. Against the Salmonella honeypot, only 10 arrive when it asked for 1,000, so the check fails and the transaction reverts. Trust the balance, not the event, and the trap springs harmlessly. Here's the fixed test, the same frontrunner, the same 1,000 token move, but now routed through the SafeReceiver that verifies the real balance change. We expect it to revert. Run it, the SafeReceiver pulls, checks the real delta, sees only 10 arrive where 1,000 was promised, and reverts with short transfer. The honeypot is caught before any money is committed. Same token, same trap, and one balance check defeats it. Now confirm on chain. And on Sepolia, the same defense live. The SafeReceiver tries to pull 1,000, checks its real balance, finds only 10 arrived, and the transaction reverts with short transfer. The honeypot moved nothing it could keep. Verify the real balance instead of the event, or better, keep your profitable transactions out of the public mempool with private order flow, and the generalized frontrunner has nothing to copy. 3 acts, 3 ways each: diagram, test, and live on-chain. Just a quick recap. A generalized frontrunner copies any profitable-looking transaction without understanding it. A honeypot like Salmonella exploits exactly that. It emits a transfer event for the full amount, but for anyone who isn't the owner, only 1% actually moves. The copybot trusts the event, spends gas and capital, and gets almost nothing. The hunter becomes the prey. The defense is to never trust the event, verify that your real balance rose by what you expected, and revert if it didn't. And the strongest real defense is private order flow, so a copybot never sees your transaction at all. Don't copy what you can't verify. A quick note, rebuilding these mechanisms safely and explaining them line by line takes real work. If it helps you, the wallets are on screen and there's a Ko-fi link below. Every tip funds the next breakdown. Thank you. And that's the Salmonella honeypot told in full. How a generalized frontrunner copies profit it doesn't understand. How a lying transfer event turns that greed into a trap and the one check that defends against it. Each act shown on a diagram in a test and live on a public chain. Next episode, another MEV mechanism built from scratch and then defended. Subscribe so you don't miss it. Tell me in the comments what to break down next and I'll see you there.